Imagine leaving Earth's blue-green glow behind and watching our planet shrink to a marble. The moon sits only 384,000 kilometers away, yet Apollo still needed 3 days. That short hop tricks intuition about distance. The real solar system is enormous. To understand travel times, forget straight lines. Every planet orbits the sun on a stretched ellipse. Sometimes it is nearer at perihelion, sometimes farther at aphelion. Each world also moves at a different speed, so your destination is always sliding away. Every night, when light from the planets reaches your eyes, you are watching this celestial traffic in motion. The same gravity that holds you to Earth choreographs their paths. Interplanetary navigation is really about learning that choreography well enough to arrive gently. To reach another planet efficiently, missions usually follow a Hohmann transfer. One engine burn stretches the spacecraft's orbit so it just intersects the target's path. Gravity assists then fine-tune speed and direction by skimming past worlds and borrowing a sliver of their orbital energy. So Mercury, the closest planet to the Sun, should be quick to reach, right? Point the rocket inward and floor it. Except every real mission discovered something infuriating about getting there. Mercury's orbit is wildly eccentric, so its distance from Earth swings between tens of millions and more than 200 million kilometers. To match its motion, spacecraft must repeatedly slow down relative to the Sun. That braking costs so much energy that fast trips become painfully inefficient. Past missions reveal the price of doing it properly. Mariner 10 launched in 1973 and needed about 6 months, using Venus for a gravity assist, just to make flybys. Messenger took 6.5 years and several planetary swings before finally sliding into Mercury orbit. High speeds are not the real challenge. To orbit Mercury, a spacecraft must arrive slow enough for the tiny planet to capture it. In near vacuum, that means long engine burns, huge fuel loads, and surprisingly gentle, months-long spirals instead of quick dives. When the destination shifts to Venus, everything looks easier. Its orbit is nearly circular, and it regularly comes closer to Earth than any other planet. At inferior conjunction, the gap can shrink below 40 million kilometers, turning Venus into a brilliant beacon in our sky. But if Venus can be so close, why have missions taken anywhere from about 110 days to nearly 200? The answer hides in one critical choice every spacecraft must make on arrival. The key difference is whether you simply fly past or stay. Fast trajectories like Mariner 2 reached Venus in about 110 days. Orbiter missions such as Pioneer Venus and Venus Express accepted 4 to 6 month cruises to arrive slow enough for capture. Reaching the surface is another story. Venus buries landers under 92 Earth atmospheres of pressure and temperatures above 460 degrees Celsius. The Venera cameras survived barely an hour. Long-term exploration will probably happen from orbit or floating platforms in the cooler upper atmosphere. For Mars, the question becomes personal. It is the planet humans are most likely to walk on first. Yet even at a close approach of 56 million kilometers, light takes about 3 minutes to arrive. At worst, signals crawl for over 20 minutes. With chemical rockets on efficient Hohmann transfers, Mars trips last around 9 months one way. Launch windows open roughly every 26 months. Any crew would spend more than a year away from Earth, living inside a metal cylinder with our planet a pale star. But powerful reusable rockets like Starship promise faster, cheaper launches to Mars. If they work as designed, the real barrier stops being distance. It becomes something far more human. Shorter transits help, but they do not erase the challenge. Crews must bring air, water, food, shielding, and redundancy for every week in space. Isolation, confined living, and delayed communication turn a fast Mars voyage into a long test of human resilience. Farther out waits Jupiter, a giant without a solid surface but rich in science. Its storms span continents, its magnetic field dwarfs Earth's, and its moons form a miniature solar system. Europa, Ganymede, and Callisto may hide global salty oceans beneath ice. Jupiter's distance from Earth swings between about 590 million and 970 million kilometers. Pioneer 10 took roughly 640 days to reach it. Voyager 1, on a faster trajectory, arrived in less than 2 years, then stole extra speed by surfing Jupiter's gravity. If we extend efficient orbits to crewed missions, a one-way trip to Jupiter could take nearly 6 years, supplying 4 people with food, water, Oxygen and spares for that long demands enormous mass. Radiation shielding and psychological support add even more weight. And beyond Jupiter, Saturn waits more than 1 billion kilometers away, wrapped in rings. Sending humans that far seems almost absurd. Yet robotic explorers already hint at something that keeps pulling us outward. Saturn orbits between about 1.2 and 1.7 billion kilometers from us. Voyager 1 needed just over 3 years to fly past in a rare alignment. Cassini took 7 years, trading speed for the right arrival velocity to break into a long, detailed orbital tour. A human trip to Saturn might take 8 years one way, depending on assists from Jupiter. That multiplies life support, shielding, and redundancy until the vehicle becomes mostly propellant. For now, robotic scouts like Cassini and future landers on Titan carry our curiosity instead. Beyond Saturn, the ice giants Uranus and Neptune circle in the cold. Their blue-green colors come from methane absorbing red light. Uranus spins on its side with a 98-degree tilt, while Neptune hosts supersonic winds and shifting dark storm systems. Because Uranus orbits almost 3 billion kilometers out, even efficient paths are long. A proposed Uranus orbiter and probe would launch around 2031, swing past Jupiter for a gravity assist, then cruise about 13 years before finally arriving to drop an atmospheric descent module. But Neptune lies even farther out, more than 4.3 billion kilometers from the Sun. Only one spacecraft has ever seen it close. The numbers for a future orbiter sound almost unbelievable. Voyager 2 reached Neptune in only 12 years by stacking gravity assists, but it flew past too fast to stay. An orbiter would need huge fuel reserves to slow from interplanetary speed. For crews, gentle deceleration could stretch braking alone over several years. Even beyond Neptune, Pluto circles on an elongated path from about 30 to nearly 50 astronomical units. New Horizons, a compact fast probe, needed 9.5 years to reach it. A heavy crewed spacecraft might take 35 years or more each way. In all these examples, far is not just kilometers. It is energy. Changing orbits means changing speed, and every extra kilometer per second is expensive. Flybys might reach Jupiter in about a year, but orbiters accept nearly 6 years to slow sufficiently. New propulsion ideas aim to shorten these times. Solar electric thrusters sip propellant while pushing for years. Solar sails and laser-driven sails ride light itself. Nuclear reactors could power continuous low-thrust engines, reshaping missions from decades into something closer to human careers. Each minute a probe spends crossing space can return centuries of knowledge. The same gravity shaping your body keeps planets in their orbits. Here on the universe and beyond, every destination is really a lesson about motion. Which world would you choose to visit first?